Hello, my name is Sean Law. I'm a person who graduated from college. The only thing I learned in college is that I know absolutely nothing. To remedy this malady, I am sitting down with professionals and educators every so often to try to learn more. Today, we have with me a high school educator of physics by the name of Mr. King. So we're going to talk about some physics and hopefully learn some more. First question for you, Mr. King.
Yes.
Are you in fact related to Stephen King?
No.
That's really upsetting. I think
I agree.
You lied to me in your emails.
I wish I was related.
Why? Okay, fine. Moving on. So, not Stephen King. All right. This week we're going to be going over how we each and every day actually interact with time travel, like real time travel.
Yeah, absolutely.
So, just movies aside, is time travel possible? Because you sent me this hefty packet of information.
Yes, it's absolutely possible.
Okay. Is it possible to not travel through time at all on the converse side?
Well, I mean, we're all sort of traveling through time at 1 second per second.
But can we not at all?
I guess perhaps in the inside a singularity, like a black hole, time might stop. I mean, when you die, time kind of stops.
Okay.
But no, not really. I think time is kind of a constant.
So how does one time travel, or how does this time travel that we're actually talking about work? Which we kind of see in movies and what we think about as...
Sure. What I'm more interested in discussing is the time travel that is actually possible, if not probable, which is time travel into the future.
Okay.
Time travel into the past would be more science fiction, although there are ideas about how we could create some sort of time machine-like thing that would allow us to travel at least back in time to when the time machine was created. What I'm interested more in talking about is time travel into the future based on moving really fast compared to the speed of light, and also time traveling based on being in a different gravitational field.
Okay. So gravity relates to time.
Yes, absolutely.
So mass... So has anyone actually, before we get into all the nitty gritty, has anyone actually successfully time traveled, gone into the future or something?
I mean, it depends on what your criteria are, really. I drove here, and while I was driving here, I was traveling into the future slower than you.
Time dilation. How's that?
Well, yes. I mean, anyone who's traveled at significantly high speeds, especially for extended periods of time, have traveled, have aged slightly less than the rest of us.
Record for time?
The record holder for time travel is a Russian cosmonaut named Sergei Krikalev, who spent over 800 days in orbit around the Earth. And aged about 20 milliseconds less than the people on Earth. So
that doesn't seem like it should count. I want to see at least 24 hours.
I mean it's I think 24 hours would be possible with faster speeds, longer stays in space.
So speed has to do with. Does that mean the Superman movie actually has some legitimate physics when he spins around the world really fast?
He goes backwards in time though.
Okay.
Right.
So backwards in time is out of the question.
I don't want to say it's out of the question, but that's much more science fiction than science fact.
Okay.
But
going into the future,
science fact
probable.
It's absolutely possible.
Okay.
It has happened.
Okay.
It is something that we deal with in our everyday lives.
Okay.
One way or another. Yeah.
Interesting. So, just to get into the nitty gritty of things, how does light and gravity actually play into time?
So, light is really the main thing. What seems counterintuitive is that the main thing that's a constant in the universe is the speed of light. Time seems like it's constant. You know, an hour for me is an hour for you, and that's just a coincidence because we're on the same planet, traveling the same speed. The speed of light is the thing that is actually a constant. For every observer...
So if I was on a different planet, I would be traveling through time at a different rate.
Perhaps.
Okay.
If that planet had a stronger or weaker gravitational field, time would be slightly different for you, either faster or slower than it would be on Earth. But the main thing is that the speed of light is what's constant in the universe. So for every observer, no matter where they are, no matter how fast or slow they're moving, light always appears to be going the same speed for any observer. And that seems counterintuitive. You know, imagine if you're driving down the road at 30 miles an hour and threw a baseball, you know, forward through the sunroof at 10 miles an hour.
Okay.
Right, that ball looks like it's going 10 miles per hour to you. And to a pedestrian on the sidewalk, that ball looks like it's going 40 miles per hour. The speed of the car plus the speed of the ball.
Now, my real question is, how much brain damage would it actually cause for whoever it hits? Because I assume we're picking somebody.
Sure. Some damage probably.
Okay.
But that's not true for light. No matter where you are.
You can't throw light out of a window faster than it's already going?
No. Light always appears to be going the speed of light, which is roughly 300 million meters per second.
That's not that fast. So, time is relative. I believe this is talking about Einstein's theory of relativity. No?
Absolutely. Good old Einstein.
Okay, so I'm not going to pretend to understand this. I feel dumber for looking at it. It scared me. I had to change my pants afterwards.
Okay.
Help?
Sure. I mean, it's not easy for anybody to understand, myself included. So Einstein has there's two theories of relativity. There's special relativity and general relativity. We can start with the special theory of relativity.
Okay.
And that's where the main idea of time dilation comes in, based on the relative speed between two objects.
Okay.
Yeah, I'm sorry.
Yeah, this is
Yeah.
shouldn't say. This is really complicated. We actually have to now refer back to the notes we wrote because we can't just talk about it off the top of our heads. For those who are wondering how complicated this may or may not be if you're not a physicist by trade. We somebody who spent years of their life dedicated to studying this can't just ramble on about it. This is going to be interesting. I'm excited.
Good stuff. All right, so a lot of what Einstein talks about is different frames of reference. Two different points of view in terms of when things happen, where things happen, the way that time is flowing. Think of it sort of like this. You know that feeling you get when you're on the train and you're not sure if
you don't want the person to sit down next to you because they look really sketchy?
That's always the feeling you have. Yes.
Okay.
Yes. I'm thinking more when you're at a station.
Okay.
And you're not sure if your train is moving backward or the train next to you is moving forward. That weird sensation that you get. Right. And that's a lot of what Einstein would be talking about. So, you moving forward is the same thing as the other train or someone else moving backward. They're essentially the same thing. Okay.
What?
They're the same thing.
I need to lie down. What? Okay, sure. Let's go with that.
All right. So, if you have, let's say, a stationary frame of reference.
Okay.
And you have a moving frame of reference. We can stop saying frame of reference. You have a stationary person.
There's a guy standing, and then something's moving past him.
Absolutely. Right? Each one of those people are going to observe the other person's clock. Let's say they have a big old clock.
Big old clock above their heads.
Right. moving slower than their own.
Okay. I'm assuming they're like Flavor Flav clocks.
Sure. Yeah, they could be wearing a Flavor Flav clock.
Okay.
That would be...
So there's 10 Flavor Flavs in like a field, and all of them are moving.
Sure. I mean, it's easy to think of probably just 2.
Okay,
right?
So one's moving, the other's stationary, and they each look like the other's is moving slow.
Right. Scientists really like using trains as an example. I don't know if that's like a nerd thing.
Okay.
Like trains. But imagine...
I'm going to assume so.
Imagine a person standing next to the train tracks with their Flavor Flav clock, and someone on the train that's passing them.
Okay.
Also has a clock.
Yes.
Right?
Timely references, by the way. That's what we have on this show.
Yeah. So they'll each observe each other's clocks to be moving slower.
Okay.
And it has to do with the fact that time is not constant in the universe.
Mm-hmm.
The speed of light is constant in the universe. And the real issue is that the two people aren't they're not observing things to be simultaneous the way that you would expect.
Now, I was looking through your notes. Is this what you call the twin paradoxes? Because that just sounds like a really awesome Doctor Who episode, or a really boring Star Trek episode. I can't tell which.
Okay. I mean, yeah, it could be a sci-fi episode. No, the twin paradox is actually not even really a paradox, but it's called that, which maybe is a paradox in itself. So
okay.
Imagine two people, twins.
Okay.
The idea being that they're the exact same age.
Mm-hmm.
Right? One of them remains on Earth,
Mm-hmm.
and one of them is an astronaut and travels through space. So they get in a spaceship and they travel away from the Earth at a very, very high speed, some significant percentage of the speed of light.
Okay.
And they travel away for however long you want to say, a year.
Okay.
And then they stop and they turn around and they come home for
Alright.
a year. Now that whole time, if they could observe each other, they'd both be observing each other's clocks to be moving slower. And so when the astronaut twin gets back to Earth, the question would be, how old are they compared to each other? If they both saw each other's clocks running slower, are they still the same age? Is the person that traveled maybe half the speed of light older? Are they younger?
Okay.
And the paradox is broken down. It's not a paradox because the astronaut twin
Mm-hmm.
experienced an acceleration, right, which is different. The two frames of reference are not identical. Someone stayed on Earth with basically nothing happening to them,
Mm-hmm.
and the other brother was in a spaceship, accelerating up to a really high speed, decelerating, slowing down back to 0, and then accelerating back home. And it's that acceleration that really makes them the moving frame of reference and makes that twin the one that has time pass slower for them.
So does this explain the movie Twins with Schwarzenegger and DeVito? Because I assume Schwarzenegger just went to space and became really awesome, and that's how he got the really lame twin. Is that he also looked like Danny DeVito and then became awesome, or am I just way off?
I don't remember any time dilation in that.
Okay.
I think it was more genetics.
Okay.
I don't know.
So genetics
It's
is
been
not time
It's been a while
dilation.
since I've seen it. I don't think so.
All right, just
Yeah,
check.
different subject. I
You
think.
sure?
I don't want to say I'm positive about anything.
That's fair. So, the faster you go, the greater the time dilation. Does that... So, we already went over the Superman movie. He was going back in time. That's impossible. How realistic are some movie physics to, like, theoretical physics? Is there any film that actually got science remotely correct? Like, Back to the Future.
No.
Just
traveling back. They're traveling backwards in time, forwards in time. That's...
Doesn't work.
Yeah, it's cool, but science fiction.
Planet of the Apes.
Planet of the Apes. Whatever someone might think about that movie as a whole, the science of that movie, the time travel aspect of it, 100% at least probable, possible rather, if not probable.
Okay.
There's nothing to say about
Monkeys taking over the Earth.
Right. No comment on apes evolving and speaking English.
Because I feel like primates already had their time, lizards had their time, or I guess birds as well. I'm waiting for fish people. Like that's what I'm banking on. Because we're primates now. We have the Earth. I assume the next step is fish. Fish are going to be next. I'm welcoming our fish overlords, so I do not end up captive and thrown into a zoo. Glub, glub, glub.
So in Planet of the Apes, Charlton Heston and the other astronauts are traveling through space, and something like, I think, 18 months passes for them. They go into some kind of stasis,
and
which is, I don't know, real or not, I'm not sure.
Yeah.
And they find this planet, and spoiler alert, it's been like 40 years, so whatever.
Interstellar?
Interstellar, another example of that, yes. And I think in Interstellar there's a couple of types of time dilation. They are traveling, it's the Endurance, I think, is the ship. They're traveling very fast. And so that itself, again, just like the twin paradox,
is time dilation, and then when they
time for them is going slower than time for people on Earth. And then in Interstellar, there's also the scene where they go to the I think they call it Miller's planet. Mm-hmm. It's the planet that's really, really close to the black hole.
Yeah.
It's covered in water, and time dilation happens in that aspect because not so much having nothing to do with speed, relative motion, but the gravitational field itself.
Okay. So with that, from the sounds of it, and I just want to make sure I'm getting this correct. Mass affects gravity, correct?
Mm-hmm.
So gravity affects time.
Yes.
So with this mass idea, does that mean Honey Boo Boo will be preserved for future generations to enjoy? I assume this is the case, as I can't think of an actual rational science reason for the existence of this, what I can only call asteroid or small moon.
Possibly.
Excellent. I'm excited to see more white trash reality TV. I believe we're all excited. So with this as well, talking about black holes, does this mean Alphaville should take up residence in a supermassive black hole?
That's certainly one option.
Again, timely references, people. That's what we have. 80s hits. Timely. Right. So, and you were going over that there's the potential for, like, the greater the mass and gravitational pull, the longer you'd be able to stay alive. Or the slower time goes.
The longer you'd stay alive compared to someone
on Earth.
Let's say if that's our reference point. The human body is still going to age, just like it normally would. To you, regardless of your situation in terms of speed or gravitational environment, you're going to age. You'll live 80 years or whatever that is. But your 80 years wherever you are might be 100 years on Earth, or 1,000 years on Earth, or 1,000,000 years on Earth. And so in that way, you're traveling into the future.
Yeah, because I was reading, like, in a supermassive black hole, you would be 146 days younger, which is just that kind of blew my mind.
Right, not in it, but if you were near it,
okay,
right, in its gravitational field, that really strong gravitational field would cause time for you to pass slower than for someone on Earth in a much weaker gravitational field. So, if a year passed on Earth, a year minus 146 days, whatever that is, would have happened for you.
So this was the part that tripped me up when I was looking over your notes. You said that we deal with a more real sort of form of, and I use real more in the terms of actual time or time dilation that I wasn't expecting on a day-to-day basis, I should say. Like all time dilation is real, I guess, but
right.
I was not expecting, but GPSs actually have to use time dilation all the time.
Absolutely. If it weren't for our if somehow we created a global positioning system without ever learning about relativity, which I guess would be possible, it wouldn't work. So the way GPS works is there are something like 24 satellites in orbit around the Earth, and you find out your position by getting a signal from 3 or more satellites. The satellites basically send out a signal that says, this is satellite 1 or whatever, and it's 5 o'clock. And then when you receive that signal, right, you might receive that signal at like 5:01. Mm-hmm. And so you know you're a minute away from that satellite, which equals some distance based on the speed of light.
Yeah.
And if you do this with a few satellites, you can kind of it's called trilateration. You can figure out where you are. It's the same way same way scientists figure out where the epicenter of an earthquake is.
Okay.
And that's great, and it works really well. However, satellites are moving faster than we are because they're high up in space and they're orbiting the Earth, and they're also in a weaker gravitational field. So as you get farther away from the Earth's gravitational field gets weaker, and so both of those effects, the relative motion time dilation and the gravitational field time dilation, affect the satellites. So the satellites are moving faster than we are. So in that sense, time would go a little bit slower for them. But we're in a much stronger gravitational field. They're in a weaker gravitational field. And so time goes faster for them. So what this amounts to is that an atomic clock on a satellite, one of the GPS satellites, ticks faster than the clock in your GPS device, your phone, let's say.
And so it's doing a math equation to
right. So not only do we have to say, okay, it took so many milliseconds for the signal to get from the satellite to the Earth, but the time on the satellite, 5 o'clock on the satellite is not the same thing as 5 o'clock on the device. And so your cell phone or your GPS device, whatever, does a relativity calculation to account for the fact that those satellites, time is passing differently on those satellites than in your phone.
Okay.
If it weren't for that correction, GPS devices would be off by many, many miles by the end of the day. Thousands of miles by the end of the day.
So I can speak today. So cartographers are the new time travelers.
Perhaps.
Well, that's actually a really disappointing note to end this conversation on.
Sorry.
Well, thank you for just being a major letdown for not being related to Stephen King, and that possibly the weirdest geographers are actually the coolest time travelers. I guess we'll have you back. That was really upsetting. I feel really let down by science now. I guess thank you. All right, now leave my set. So that's science. I would like to thank Mr. King for coming on to the show. If you're interested in what we were talking about today, you can check the show notes below for links and more information. If you'd like to come on the show and you're an educator or professional, we'd love to have you. You can please find our email below. Also, if you have any comments, questions, or concerns, there's a different email for you. If you'd like to support the show, you can visit our Patreon account, subscribe to the channel, or watch those really annoying 15-second YouTube ads then don't click skip. That'd be great. I think we get paid more when that happens. I hope we get paid more when that happens. Let's just pretend we get paid more when that happens and don't click skip. Cool. Alright. Glad we have this agreement. I'd like to thank Rec Films and Ryan Chattel for helping us out. With all that said, be good.